Hello, folks. Welcome, and thanks for joining us for this presentation on implementation of iOLab activities for lecture demos, studio, or lab. And actually, I think we can add another category to that for student at-home activities as well. My name is Todd Ruskell. I am a teaching professor at Colorado School of Mines. I've been doing this for a little while. And what I'd like to do is first talk a little bit about the background and the context in which I've been using iOLab, and then we'll get into what these activities really look like. So the context. So what does physics at Mines look like? We're a relatively small state school, about 5,000, 6,000 undergraduates. We're mostly science and engineering, and everyone at this institution takes Physics 1, and nearly everybody also takes Physics 2. We teach our courses in what we refer to as a hybrid studio format. Students do some pre-class readings, then they come to a 50-minute lecture/discussion, which is very heavy with peer-to-peer learning, iClicker questions. It's a pretty active kind of lecture. That's kind of why we call it a discussion. Then the next day, they come to a studio session. This is an hour and 50 minutes long. They work in groups of 2 or 3. We deliver content electronically to the students, so each group can work independently and progress at their own rate. And the studio is, for us, a combination of a traditional lab and recitation. Sometimes we're doing a fair bit of problem solving. Sometimes we're devoted almost exclusively to some kind of hands-on experiment. And sometimes it's really a combination of those two things. And for us, in this studio is where we happen to use iOLab in our course. But iOLab can be used, pretty much anywhere.
So at Mines, we started looking at using iOLab back in 2015, 2016. In 2015, we realized that our existing computer-based infrastructure was not going to work for us anymore. The main interfacing components were no longer supported. In fact, they were no longer being manufactured. And so we were going to either have to upgrade that within the existing vendor or change vendors or do something. And about that time, iOLab was starting to make a few noises in its introductory phases. So we had had some contact with Matt Sellens, and in the fall of 2016, we managed to acquire some prototype iOLabs. We had a couple of seniors, physics majors, who were very interested in exploring the iOLab and what it could do in our studio, how we could utilize that. They also were also TAs for us. And so they were ideal candidates for evaluating iOLab. That project, lasted for the entire year. And in the spring of 2017, they presented their results to our team of faculty involved in our introductory physics sequence. And based on that, the faculty decided that we would go ahead and make the switch to utilizing iOLab for our Physics 1 and Physics 2 courses. So that summer, we purchased a lab set of iOLabs, and we have been using them ever since. So one of the things that is important in there is that we did, in fact, the way we use iOLab is as a lab set. So we have 2 iOLabs in every station. That allows us to a little more flexibility. We can do things like have each group do collision experiments, for instance, and so forth. I'll point out that with our 44 stations, that means we have 88 of these iOLabs operating simultaneously, and we have absolutely no issues with crosstalk communication or any of those things. So it's pretty robust even in a large number implementation. So depending on what kind of scenario you have, you shouldn't have to worry about that. So what can iOLab do? Well, it can measure just about anything that you might need to measure in a Physics 1 kind of lab. It has force sensors. It has a wheel sensor for measuring kinematic quantities. You can measure magnetic field. We can measure light and sound, rotational motion, as well as temperature and pressure. It also has voltage measurements. It has individual pins where you can access current voltage and make some measurements. So it's really ideal for this intro kind of course. It's also really versatile. In addition to being able to measure all of those quantities, it's pretty inexpensive, and you can use it in a variety of ways. It can be used as a single setup, as a lecture demo kind of scenario, if that's what works in your setting. If you have a lab or a studio environment, you can use this in terms of having a class set that people will come in and use and then leave the equipment behind for the next group to work. You can also use this as an individual kind of thing. University of Illinois and others have taken this approach where you can have the students each individually purchase an iOLab device, and they can then do at-home activities. They can, work with classmates, work with their roommate, and do things on their own outside of class. And depending on what you might want to do, you can maybe even have them bring the iOLabs then into a particular class so that they can participate in in-class activities with the iOLab as well. So the fact that it is inexpensive means we can use this in a huge number of ways. As a footnote, I will add that because iOLab is completely open source, that maybe opens the door for a possibility that in some upper level classes, in some disciplines, you might be able to use iOLab to take data for some other kind of experiment that someone's developing, or have students experiment with coding and interfacing this device. We're not going to talk about that here, but it's a neat idea and something to be thinking about in terms of how flexible this is. So what I really want to talk about today are the IL activities for college physics in Achieve. So some of you may be familiar with the college physics textbook, and if you're not, I encourage you to become so. I'm not biased, of course. But one of the things that we want to do for college physics is to tie in lab activities that really mesh well with the college physics textbook, so that things can maybe march in lockstep, or if not in lockstep, at least are not completely discrete from the college physics textbook, if you're using that. So we have about one of these activities per chapter. Some topics don't really lend themselves to use with an iOLab, so we don't have an activity for those. Each one of the activities lists the required equipment, lists the purpose of that activity, of course, and as it also lists some potential gotchas that you might have as you try to implement that activity. And then for the student perspective, we have three main steps that we sort of guide the students through: think and predict, experiment, analyze, and process. So as we think about how you might want to implement each of these activities, you may or may not want to utilize all of the think and predict or all of the analyze and process pieces that come into play. But that's really up to you. We want to try to make these activities pretty flexible, and you'll see some of that flexibility as I go through one of those. Before we do that, I thought I would give a little more detail about the activities that we in particular don't have that in the chapters of college physics. So gravitation is a pretty tough one. You can't really measure big G kinds of things with our IO labs. We also don't, at this point, are not planning activities for Chapter 16 on electric charge, forces, and field, for Chapter 22, electromagnetic waves, and we do not currently have activities planned for the modern physics section of the textbook. We do currently plan to have activities, an activity for every other chapter of the book. So you can, if you have a limited number of lab times, as most of us do, you can kind of pick and choose which sets of activities are most appropriate for what you want to emphasize in your course. All right. With that, I would like to go ahead and dive into show you a little bit what one sample activity on Newton's third law might look like. So to do that, I'll hopefully succeed in flipping over to this Word document. The idea of these activities is to give you a framework around which you can build your own activity. If you use something as a lecture demo, you maybe don't need a whole lot of instruction. If you are using something as a lab, depending on where in your course sequence that lab occurs, you may want to provide more guidance or less guidance to your students. You may have more or less time to work on a lab. You might have a 3-hour lab. You might have something more like a 2-hour block like we have at Mines, or maybe it's an activity that is only going to take one fraction of a 2-hour time block, like we happen to do a lot of the time. And so we don't want to wedge and force a particular structure upon you. So instead, we give you a variety of things that you can then construct into your particular context. So we start off Newton's third law. What's the purpose? In this particular activity, explore the forces two objects exert on each other when they collide. All right. We list the required equipment. It's a collision, so we need 2 iOLab devices. We have a couple of force plate accessories and some other items which you may want to incorporate or may not, again, depending on what you want to focus on and how much time you would like students to spend on these activities. And then list some potential gotchas. So some things that you need to be aware of. One of them is that the force sensor on the iOLabs has a maximum force of plus or minus 10 newtons. There's a limit of the resolution. But in particular for this activity, one of the more important things is that the force data rate is only 200 hertz, or every 5 milliseconds. So when you zoom in on data that you may have collected, it might look like the force measured by one iOLab does not occur at exactly the same time as the force exerted on another iOLab. And that's artificial. That's due to the data rate. Okay. The other thing that this means is that it's possible that the plots might not actually record the peak force exactly. So you need to take that into account. One of the things that I like about the iOLabs is that unlike some of the other lab equipment that is out there, it's a real device. They don't go to huge effort to make everything frictionless, for instance, and so on. And so this brings some of the reality of the experiment to the forefront. And one of the reasons I really like this is that it seems like there are always a fair number of students who like to divide things as, well, there's the physics answer, and then there's the real world answer. And I guess I'm in physics class, so I better give the physics answer, even though that has no bearing on the real world. And I think iOLab really helps bring those two worlds together, bring those two worldviews together for students. And so some of these gotchas, yeah, they're gotchas, but I think they have served a very important pedagogical purpose. All right. And then, of course, you want to make sure to calibrate things. So for the students, what do you want to do? Well, you might want to have them think and predict at the beginning what's going to happen and why. If you're doing this as a lecture demo kind of scenario, maybe you ask some of these questions as iClicker questions. If you are, or maybe you ask some of these questions as just-in-time teaching kinds of questions before students come to class. That's a possibility too. If it's in a lab, then maybe this is sort of part of their initial lab report. And you don't have to ask all of them, right? These are just some suggestions for questions or think and predict. And maybe you actually have some other think and predict questions that you would prefer to ask instead of these. So again, the flexibility is what's key. All right, then for the experiment, we give a brief set of experimental directions. We're assuming here that you and or the students are familiar with the iOLab device and somewhat familiar with the software. So this is not a step-by-step, every click kind of set of directions. If you need to provide those, then I'm going to let you do that. Hopefully you only have to do that maybe for the first or second lab. But that, again, allows you to tailor this toward your own students. So what do we need to do? If we're going to have a collision, we need to attach something to the force sensors of the iOLabs. We need to connect those iOLab devices. We need to calibrate the force sensors. That's always super important. Then tell the iOLab software that we want to measure force, and then run the two iOLabs into each other. Start with one stationary and push one into it. All right, and see what you get with your force plots on the iOLab. Then you might want to change the masses just to see if the relative masses somehow changes these Newton's third law pair forces. We know that one of the common misconceptions of students is that the larger object pushes harder on the more massive object pushes with more force onto the less massive object, and the less massive object exerts less force on the more massive object. Well, we can get at that misconception by piling on some masses. All right, what those masses look like depends on what you might have in your own institution, what kind of resources you have. Maybe students might think that it's different if you have one object stationary and one moving. So try it together with both of the iOLabs moving, maybe in a head-to-head collision and maybe in a rear-end type collision. All right. Maybe replace one of the plate attachments that got cut off with a spring, and see if that makes a difference. All right. So a variety of things that you could do, ways that you could extend this experiment to see what happens, and maybe, or maybe have the students decide, maybe one of your questions is, or one of the steps in your experiment would be, after you have one stationary and one moving, ask the students, how would you extend this? What other experiments might you do? And have them come up with these things on their own. That would be great. You could also have students do this completely outside of class, right? Pair up with a classmate who has an iOLab, so they each have one iOLab. Now they've got two, and the two of them can work together and do this. Or maybe you go all out and you ask the two students to get together and come up with an experiment to show or verify, confirm Newton's third law, all on their own. And you don't really give them much at all other than, hey, you've got these two iOLabs and you know what they can measure. So there's a lot of different things that you can do. After you do the experiment, then we want students to analyze and process. So in this case, Newton's third law is a pretty straightforward thing. What seems to be true about the magnitude of the force of object A on B and B on A? Hopefully, they will come to the conclusion that no matter what happens experimentally, those two forces are the same, but they get to play around with the devices. So that is a quick run through of what just one of these activities might look like. If you want to turn this into a full-fledged lab, you can have students do multiple runs, take data, estimate uncertainty. You could do all of those things. But we know that every institution has their own, way of introducing those ideas and how they might want to do that. And so again, you can add those extra pieces around this activity, which is going to be available in a completely editable form. So you can download this and copy and paste the pieces that you need and that you want to use. With that, I will stop here and ask if you all have any questions.